Okay, so I will start my second session about model simulation of large-scale integrated modular CPS. So I talked about modeling and simulation a lot last the first session. Now I go more into large scale and also integration and modularity a bit. And tomorrow I will talk more about modularity and integration of models. So complexity and dependencies. Typical properties of an aircraft actual development is that we have process complexity and we also have the technical complexity. Like sustained engineering is that in Sweden we have a model, business model, that we are able to upgrade the aircraft frequently. So we don't do a mid-life upgrade like they usually do in the States, for example. Here we do every second year upgrades, so we do sustained engineering, like a agile, more or less. And we have growth potential, of course, so when we buy new hardware, it has to be potential to grow several upgrades. It's long life cycles, of course, for the structure is up to 40 years. We need to have a product family approach, so we can have different product variants for different customers without starting a new program every time we need a new customer variant. There are many suppliers, of course, and that is very similar to the automotive industry. There are suppliers all over the world. So integration is one part there, and of course there are a lot of regulations and standards, both for flight safety, critical parts, but also according to security and other stuff. And on the technical complexity, there are a lot of software, software-intense system, several million of lines of code, more than 30 computers integrated, databases. There is an advanced on-condition maintenance system, so we can follow up the lifetime of several equipment and monitor when it's time to change them. And of course we need redundant backup systems. That is a big difference between the truck or automotive industry. If a major failure happens in a car, you slow down and park on the side of the road. It's not possible to do in the air, so for the critical parts we need backup systems all the time. This is a single engine application, and that is not so common. Usually you have two engines to rely on, so a single engine application is more critical. You really need to trust that the engine is working and the control of the engine is working all the time. And there is also roll equipment. I don't know if you know the JAS concept. Jakt, attack, spaning is in Swedish. That means that you can have different roles in the air. So you can put up different loads, like weapons and cannons and fuel tanks and everything. So you can have different. You can combine and have different configurations on the aircraft. One configuration in the afternoon and one in the evening. Yeah.
By on-condition maintenance,
Yeah.
do we? I think it's during the flight. If something goes wrong,
Mm.
can we update the software? Or?
No, not yet anyway. I will look at it, but this is more connected to that. After, I mean, a flight is approximately one hour. That's a typical flight. So after each flight, download all the data, and the technicals look at the data and see if something happens that need to reschedule the maintenance also. Yeah. So some properties of complexity. What do I mean with large scale for a CPS? So to say, related to that we have many functions in the system, many requirements, of course, from both customers and other stakeholders. There are a lot of properties and characteristics to deal with. Communication channels. We have development sites. I mean, we develop sub-suppliers, or ourselves, we develop parts all around the world. Interfaces, of course, dependencies between a lot of things, a lot of people, as I talked about earlier, and we have a lot of communication needs. This both communication within the product, but communication during development. How to handle all those? Of course, there are a lot of things to do, but typically we have to divide the functionality in subsystems and have responsibilities according to each function very clearly. Requirements, we need proper stakeholder analysis for all the requirements. Properties, here comes the modeling and simulation in. We need to simulate and understand the characteristics of the integrated product. Communication channel, typically we rely on standards, like NATO standards to get the communication reliable. Development sites, here is modularity one thing, and I will talk more about that tomorrow also, about modularity and integration of models. Interfaces, there is planning very important. I mean, you should really do a good job with interfaces so they are stable, so you don't have to change the interfaces, because that's very expensive to do late. Architecture, I will come back to architecture a bit. And here, of course, a lot of people, organization in teams and projects. And here is also important to have good team leaders and project managers suitable for the level of scope they have. Both to organize people, but also to understand the technical parts. So the team leader should be both technical and team players, so to say. And languages, of course. I talked about systems modeling language. And as I said, we're not really happy. It's not a standard that are used everywhere. So we are open for proposals of other standards or languages that could be used in cyber physical systems. So in your research, for example, you are free to come with examples or proposals. Yeah. I think you have seen these pictures before. To integrate a lot of domains, engineering domains from different departments. This is always a balance, because the aerodynamic people, they want to have a very nice, fine shape of the aircraft. So they fight against the propulsion people. They want to have a big engine and so on and so on. So here is always a trade-off. So here comes the systems engineering part. I don't know, are you familiar with the systems engineering discipline? Yeah? If I should ask you, mention one standard or one organization that deals with systems engineering, what do you think about?
You mean the standard?
Yeah, or organization. Yeah, or in COSE, yeah. Yeah. We rely on in COSE for systems engineering, and as I mentioned earlier, this ISO standard 15288 is a standard for systems engineering, organizational processes. So I will talk a little bit about the importance of systems engineering and how I see this role. But it handles a lot about to be able to integrate those engineering disciplines that are actually they are somewhat arguing, or they are in conflict when we're building a complex product. So in my view, the systems engineering is a technical or engineering discipline that handles the integration of all the different special engineering disciplines. But also it is an interface to the program and project management. So it's a lot of planning in systems engineering discipline also. And that's why it's important to have systems engineers that are T-shaped. If you remember Martin yesterday, or maybe it was on Monday, he talked about the T-shaped skills of an engineer. So systems engineer need to have a wide skill in systems engineering. I will come back to what I think is included in that. But also some depth in some discipline is very good. So you can at least talk the languages of the electronics people or the mechanics people. So systems engineering in fighter aircraft development. If you know systems engineering as such, so in aircraft engineering, the safety engineering is a very important part, of course. Then we have configuration control, requirements management, budgets, modeling simulation, information control, risk control, and all those utilities like availability, reliability, and so on. This is a long list. And then we have the writing of the systems engineering management plan. And that's something I've been doing the 5 last years, not writing all the plan, but to maintain, because there comes input from a lot of disciplines, both like those reliability and reusability departments, but also from the technical disciplines like the cooling department also, and so on. So we gather all this information on how to work in the project together in a systems engineering management plan. And those budgets is also something that sometimes is a bit forgotten or underestimated, because it's so easy to focus on the functionality of the product, but to forget the utilities or the limited resources. So typically we have a group that are focused on functions, and we put all the functions together, but when we have put the functions together, those other aspects arise, and we see, shit, we don't have enough power, we don't have enough cooling, we don't have enough bandwidth, or whatever it is. It's very difficult to predict that early in the project. So early we focus on functionality, but as a systems engineer, you should be aware of all those utilities and budgets. So I come back to this picture again. We need both people that are specific on the specific topics, and we need the global view of the product, as I talked about. So then we come back to, I talked about this, the different aspects, but the T-shaped skills, the T-shaped engineer that Martin talked about. So here, up here we have a wide breadth of knowledge across many disciplines, also connected to project management, as I said. And we have the depth knowledge and experience of one or more fields, engineering fields. And now I would like to ask you, what is the shape of your skill? How does your T look like? Is it very broad or very narrow, or is it deep, or how is it? It will not be an exam. You can just think about it. Maybe you can share it if you want to. So of course we can have several depths, or we can have just one very, very deep knowledge of domain here. We can be very broad. But I would like anyway to reflect and think about what, because if you see, when you see a product and you think, oh, might be this has a big engine. If the first thing you think of, then probably you are an engine engineer, to say, or whatever that rise. That is your preferences, your preference of details or engineering domain. So think about what is the shape of your T and what field or fields do you have deep knowledge or experience in. So please take a couple of minutes.
Like history.
Thank you. Good discussions, I think. Very good discussion this time of the day. Somebody want to share something to us? You don't have to, but it's nice. Yeah.
So my T feels more like an I.
Yeah.
So really focus on one topic, and
Yeah.
that's basically it.
Yeah.
I don't know whether it's good for my position or not, but it's the case.
Yeah. I mean, if you should be a systems engineer and work with planning, so it might be good to have some witness up here. For myself, I mean, as you grow and work a lot in a big company, you train to do the integration and collaboration between teams and so on. So I become more broad as I've been older. That's maybe normal. It is that way. I'm not really sure. Yeah, somebody else?
Well, I think I'm also fairly long
Yeah.
and thin.
Thin, yeah.
Yeah.
But in the company we need a mix of both, of course. So we need people that are very deep knowledge, and people that are very wide, like systems engineer, to say. But also people that have experience from different fields also. So that is a very good mix. Yeah, thank you. I mentioned this, but it's very important, I think, in a way that functions, that is something we want. We want to have a product with functions, so the customers or the user can use the functionality in the product. And then properties or characteristics, some of those, they emerge during integration, so that's something we don't want. This is a tricky part when it comes to requirements, because it's easy to require the functionality, but it's not so easy to usually call them non-functional requirements. It's not so easy to handle them because they are tricky, and you, for example, it comes to safety, for example. It's easy to say this should be a very safe product, it should never crash, for example, but to guarantee that is very, very difficult. So you need to elaborate with properties also on the numbers, also on the characteristics. And some things that, as I said, we maybe underestimate something is weight, specifically for aircraft and flying objects. The weight is very, very important. We need a whole department that is working with measuring the weight and controlling the weight during all. When we buy things from subcontractors and so on, there should be people for the weight department to control the weight figures and so on. Say for power and cooling, they are connected, of course, because more power you put in, usually the more cooling you need as well. And here is sometimes a very confusing mix, because people they put up the power figures, but they don't understand that they require more cooling. I mean, it's connected to equipment and electronic equipment very much. And also we need, this is static usually. I mean, we have the fuel is decreasing, so the weight of the aircraft is decreasing during flight. But power and cooling is difficult because that's very dynamic. During startup you need more power for one equipment maybe, and depending on what you're doing on the operation of the aircraft, it's different. And those illities, as we say, like safety, security, maintenance, everything, they're also difficult to handle, and we have responsibilities and departments for all those illities as well. But they are, in some way, it's more fun to work with the functions, the functionality. And it's sometimes not so easy to get people to take responsibility for the illities. But as a systems engineer, I think we need to be very interested and have focus on the illities as well. And in large-scale systems, we often discover those problems very late, too late, in the non-functional areas. It's easy to build models that model functionality, and we can see it in a simulator and see, oh, it functions. This is the function we want. But the non-functional things is more tricky. An example is temperature. Usually we have simulator models that is handling the functionality, the behavior, but we don't take into account the temperature of every piece of the aircraft. So that's one thing that seems not so important, but in the real life, probably it's in those kind of areas we have problems later. So then we can add the temperature property in the models, but to add things and over again get the models to be very cumbersome and hard to maintain. So here we need to have a strategy from the beginning. What properties should we model as default, and what properties should we model when the problems occur? So that's a strategy. It's included in the systems engineering management plan, what kind of strategy we have there. Yeah, I will talk a little bit about dependencies. This is maybe, I think you have heard and thought a lot about this, so it's maybe nothing new, but anyway, it's so important. This is the picture that Martin showed Monday, I think it was, that a number of dependencies seems to increase all the time. And we cannot just let that go. We need a strategy to handle the dependencies, because there are too many dependencies. It's very, very difficult to develop and further develop a product. So one thing to handle it is a very, very simple example, but I will show it anyway. In the aircraft we have the electronic unit, the ECU, embedded controller, and similar is the telephone, the mobile. So here we can see that we have some kind of architecture. We have the hardware layer, we have some kind of operation system layer, and then we have the applications. And it's actually the same pattern in the aircraft. We have the ECUs, we have some kind of operating system, and we have the tasks to do the operator functionality. Like this. And if we do this in a proper way, we have a very good interface here, so we can split between infrastructure and the applications, and we can also split the applications from each other, meaning that we can develop parts of the product at other sites. We don't need a communication during development in the same way as is like more like a spaghetti. You understand what I mean? Of course, this means that we need to have very good specified interfaces. Another thing is that the hardware have long life cycle. We don't upgrade the hardware as often as the infrastructure layer or the applications. And I think you can recognize this from the mobile. How often do you buy a new hardware?
3 years.
3 years? 2 years? 2 or 3 years? Yeah. I think it's pretty common. How often do you get a new update of your operating system? Several weeks, yeah. Yeah. A couple of times every year, I think. Something like that. How often do you get updates of your applications? Weekly.
Weekly.
Yeah. And it's exactly the same pattern in the aircraft. Those kind of equipment maybe last 10 years or so. The operating system and the infrastructure we upgrade once a year maybe, or every second year. But the operational software we have to upgrade more often. And in the future we think that we need also to be more and more quicker. So we have quick loops, and they have to be separated so they can be updated and maintained autonomously or in a modular fashion. But also modularity in this way that the operating system and infrastructure is separated from the application layer. So different people can work in different sites, and we don't have the dependencies in the same way. It should also, of course, be dependency downwards, but not the other way. Yeah, and we also, if you have an interface that is used by very many, we call that a service because it serves very many applications. So the service interfaces, the interfaces called services, should be planned in very early and be very stable, so you don't have to change them, because changing a service affects a lot of applications. It's very expensive, and in the aircraft industry we have to verify, test everything over again. It's very expensive to change the interfaces. So here we really have to do a good job early in the program. So examples of those services is time, provide time in a very good precision to all the applications. Position, what position do you have now? It's coming from GPS or other sensors. And notification alert is something also that it should be centralized in the service. Communication, how much energy is remaining, or access to cameras and so on. This could be a long list. But the more central they are, the more important and the more planned it should be. So, talking about the functionality that we want and the aspects that we really don't want, we need to keep track of that. So we use a standard called, it's called recommended practice for architectural description of software-intensive systems. Anybody heard of this? No. It says anyway, for a system that has a mission and an environment, we need, or it has an architecture. The architecture is described by some kind of architecture description. And these have several views. It's organized in views. Now the views are organized according to the description. We have models and viewpoints, and those viewpoints are maybe the same as I talked about properties or aspects earlier. And here comes to the point that we have to decide from the beginning what kind of models we need to view the system through the viewpoints. And as I said, temperature could be one example that we can decide early if we need in a specific model or if we include that in our normal models that we have. Also, those stakeholders here, there are typically the departments dealing with safety or weight or whatever it is. So these stakeholders need also to be identified, but also have their own viewpoint. And here is the trick that this SysML or this language, if we had a language that could handle all those views for all the stakeholders, it should be really good, because then we can have one central model. But as it is today, it's the SysML or the languages we have, they are not good enough to deal with all the viewpoints that we need. So that's one thing, that we need different models to handle different views. And it becomes problematic if we have different architecture descriptions as well. So here I also feel, I think, that is needs some more research and proposals for how to handle the different viewpoints and aspects of the product, of the systems.
Question: this concern, is it related to requirements? Concern?
Yeah, it could be, but stakeholders could be. It could be a customer, could be, and then it's it relates to requirements. But it could also be the internal or other kind of stakeholders. Usually, I mean, if we take weight as an example, weight is a concern, and of course the customer is also interested in the weight of the aircraft, but we also have the department, the engineering department working with weight. So it could be a lot of different things. But usually we try to specify things in the form of requirements, both externally and internally. So when we misunderstand each other, sometimes we go back to this model and say, aha, your concern is this, but I thought the concern was something else. So just to describe things by this model, it can help us to understand each other better, actually. So it's a trick that we can use sometimes. I also come to how to get a balance between those the different aspects of systems engineering, because overperforming activities is waste, of course. So we do a lot of simulations or something, and it could be waste to do that. It's easy to do things that are fun or that we are good at, but we need to look at where are we underperforming, because that costs a lot in terms of quality and so on. So we have to perform this, and I have a kind of a model for that also. It says that the different activities we can do in systems engineering, like simulation, we can review things, we can do tool training requirements. It's the lowest stave here that allows us to fill water or wine or what we want in the barrel. And that is the performance of our system. So the shortest stave here decides what the performance of our system is. So if we miss to have a good configuration control, for example, it will in the end show us, oh shit, here was where the water or the wine disappeared from our system, and we cannot earn money, we cannot get the performance or the quality of the system that we had as a goal. So this is a kind of a mental model to be good to think about, and I hope when you become systems engineers, you can think about this sometimes. And once again, the common shared view is very important, and is also connected to the barrel. I mean, you should also we should have a common shared understanding of the barrel, and where do we need to put our efforts in systems engineering to get the the right and the most optimal of our engineering efforts. Yeah, I talked about this. So I think this was the thing for today. And I open for questions. Yeah.
The models that you presented that have different stakeholders
Yep.
represented, how widely used is that? Is it something that's new or is it something that's already in use?
It has been around for at least 15 years, I should say.
And in practice, how widely used is it? Fairly common, you say, or?
In systems engineering planning, I think it's used, but not among ordinary engineers, so to say. I don't think. So it's more in the planning, in the setup of programs and projects, where we decide organizations and what kind of facilities we need maybe for doing analysis, or what kind of tools we need and so on.
And the planning is often done at the management level, or?
Yeah, at the management level, but we need a combination of management and good engineers with good practice. So it's a combination, of course.
So it could be the same engineers involved in the planning phase
Yeah.
and use it in the planning phase, but then when it comes to the execution, it could be different.
Yeah, usually we have a lot of more people involved in the execution. But it should be good to go back and see why did they choose this kind of tools or this setup of facilities or whatever it is to analyze the different concerns. So you have this common understanding of also those things. Yeah. Yeah.
You've shown the hardware life cycle, the middleware life cycle, and also the application life cycle. And in general, hardware life cycle takes a longer time,
Yep.
and the middleware takes say medium time, and the application takes faster life cycle to react immediately. So if this is the case, how do we adopt the process? Because for the hardware life cycle, you may work in one process,
Yep.
say traditional waterfall life cycle.
Yep.
And in application, you may use Agile or Scrum
Yes.
life cycle. So how do you match
Hmm?
when 3 layers work in different life cycles?
Yeah, yeah, that's very good question. And it is easy for management to say we should only have one process. We should do the same because it's easier for us to understand. But then it becomes hard actually to work. So we propose that at SAAB we have different processes for those different layers. Because as you said, they are different. There are different skills involved. Documentation requirements are different, and so on and so on. So we have more agile approach up here, and more waterfall or more.
Recycle.
Yeah, and here we have subcontractors involved also, so it's another aspect of the process as well.
Yeah.
Acquisition process is involved here.
So will you follow organizational level the same process, or different layers will follow different life cycle model?
No, both, yeah. And there's also debate, of course, SAAB and other companies, I think. Should you organize the company according to these layers, or should you organize the company in skills or some other aspect, and then organize the project, the development project in this way? And I think it turns forth and back. There is no right answer to that question, I think.
Why I ask this particular question is since SAAB is more a product company, if I understand, it's end-to-end complete.
Yes.
You build a complete aircraft, for example, So I just wanted to learn, since you get something from some parts from supplier, of course, for example, electronics.
Yes.
They may work in a different life cycle process like that. And your organization may work on a different one. So how do we match this kind of unknown thing to me?
Yeah. That's also so I think that's different in different businesses, because some suppliers, they have more like an agile approach, so we're easily discussing the requirements, and we can change the requirements more easily. But others have more a contract. We sign the contract, and it goes 4 years, and then we get the things. So there are different approaches for different businesses, different contracts. Yeah. Yeah.
Any other questions? Thank you very much.
Thank you.